Hello everyone and welcome to episode 2 of our Data Vault series. Today we're going to be looking at the first sequences. So we'll be doing overviews of the create account, the login, and then the logout sequences. We'll be looking at data values that need to be parsed, created, read, saved, all of that stuff, and we'll be going into detail. We'll be creating somewhat of a pseudocode, not really a sequence diagram, something in between. But this is just going to be our basis for when we actually start writing the code. So my thought process here is that we'll go over the processes, and then once we have everything, or once we know what we need, we can then start creating code and creating the appropriate class or structures and methods and organizing it properly. Okay, so the first one will be the create account. Here, as I put, I'm just going to be doing this in Markdown. And this will be on the GitHub README page. So we have, for the create account one, we have that we are going to be taking in, so the input will be a user password. So user PWD. That's just going to be, so for example, if we, in the command prompt say create an account, we will prompt the user to enter a password, and that's all they will enter. We could do a username, but that's not really the point of this. We're not looking at creating multiple accounts. You could, but we are focusing on just creating just an account with a password. So you input the user password. So here, what we're going to have to do is, if we look at all these files that we have up here, so there are a bunch, and I can actually just go in the preview here. So we have all of our files here. So the iv.dv that has all of our iv values, data.dv which stores the encrypted data, map.dv, btree.dv, categories.dv, password.dv, datakey.dv, and those are all files that we're going to need. So when we create an account, we are going to want to create these files. So what we can do is, the goal here is not only to generate salt and IVs and the data key and hash the password, we're also going to have to create files. So step one here, I would think would be to create all files. So there's going to be, it's going to be updating. So this will be, we'll have to go back and forth. So we have iv.dv, data.dv, map.dv, btree.dv, categories.dv, pwd.dv, and then datakey.dv. So in this sequence right here, in the create account sequence, we're only going to be writing into a few of them. Since we have no data, we cannot write into data, map, btree, or categories because there's nothing to write. We don't have any password entries that we can map string names to IDs or initial blocks, something like that. So that rules out these three files. And then data.dv, we just have no data, so we also cannot write into there. But we can create them just with zero size. So the second part here will be, we're going to be generating our salts and IVs. So generate salts and IVs. And this will be what we write into iv.dv. Output into iv.dv. So all of our salts and IVs are going to be, they're going to be 16 bytes. I believe I actually forgot to include a salt, and I did actually, yeah. So I did forget to have the key encryption key salt in our list here, so we'll just add that real quick. And if you remember, so I'll just go over which all these, what they will all do. So user pwd salt is going to equal random byte 16. So we're going to generate 16 random bytes. User pwd salt will be stored in this file and will be used to concatenate with the user's password when we're generating the hash. So user pwd salt, then we have data key, or sorry, kek salt is equal to another 16 random bytes. I'm just gonna copy and paste that because we will be just generating 16 random bytes. We have data key IV, So I forgot to mention it, but KEK salt will be what we pass into the key derivation algorithm. Data key IV will be the initialization vector for encrypting the data key. Then we have data IV, which will be the initialization vector for encrypting data.dv. Map IV is initialization vector for map.dv, btree for btree, and then category for category. So we're gonna write to iv.dv user all these salts in this specific order. Okay, so that is generating our salts and our IVs, and then we output them into the IV file. So now that when the program starts up, we know where to look for all of our salts and IVs. Okay, so number 3, now that we have our data values set up, we're now going to start generating our data key for the user's password. Well, first, what we're going to have to do is process user PWD. So we need to generate the hash of this. So we're going to write into, it's going to be pwd.dv, I believe. Yes, pwd.dv. And what we're going to write into this is SHA-3 512. So the hashed version using SHA-3 512. The salt is equal to user PWD salt. And then the text is the user PWD. So we're going to write the hashed password into pwd.dv. And from now on, the program will not store the user's password. It will take it in and process it, but it will not store it. It's going to free this memory once we finish it. So we write that in, okay? And then we're also going to start generating our data key. So we need to say data key is equal to random bytes 16. So we generate 16 random bytes as our data key. And this will be the key that we use to encrypt all of our data. And if you remember last time, we broke up the login into 2 parts because we can't just use the user's password as our encryption key. So we need to break it up into steps where we use the user's password to derive our data key. All right, so we start by generating a random key. That's just going to be our 16 bytes. And then what we're going to do is we will now generate our key encryption key. So the key encryption key is equal to, we're going to call a password-based key derivation algorithm. So pbkdf2, passing in the K is equal to user PWD, the input password. Then the salt will be equal to the KEK salt. So that's what we have up here. That's already generated. And then the derived key length is equal to 32. So since we're going to be using AES 256, we want to be using a key length of 32 bytes. So now that we have our key encryption key, we can write into, this will be datakey.dv. We will call AES 256. The key is going to be key encryption key. The text will be data key. And then the IV will be the data key IV. Okay, so this third step here is more of like process user password and generate data key. So we generated the data key and then wrote it into datakey.dv. And that's pretty much all that we have to do for creating an account. We generated our files, so we have everything up here. We have all these files are generated. We have our salts generated, so we're prepared when we want to actually encrypt data. And then we also generated our data key. So we are prepared when we want to actually start taking data input from the user. So that's the create account part. Now, so we'll move on to login now. Login is going to be fun. So input here is going to be user PWD. So that's just the user's input as before. So they input a password to login. So we need to check So the login process is, I'll just diagram it out real quick. So for logging in, so we take in a user password, and then we pass it into the login function. Now, how are we going to verify that this password is correct? Well, we could just store the password on the computer and just compare the contents, but as you probably know, that's not secure, because if someone gets a hold of this, then they would have access to your password, and that's not good. So we need to encrypt it somehow. However, we can't encrypt it using a key, because then that key would have to be encrypted somewhere, and then you would have to find a data key. So you're just going to go in an infinite loop of needing extra keys when we can just use the user's password as that. That'll be our starting key. So the way we'll store this securely is using a hash function, and I've talked about this before. But the way to log in is going to be, we store, so in user, or I think it's just pwd.data vault. In this file, we have the hashed user's password. It's 64 bytes. And that's an irreversible function, so you cannot find a password from the hash. So when we generate our user password, all we're going to do is regenerate the hash. So we will hash the user's password and compare it to the contents of pwd.dv. So if the two hashes are the same, then we can reasonably conclude that the two inputs are the same. So we're going to validate. So one, validate password. So validate user pwd, and all we're going to do here is input hash is equal to SHA-3512. The salt is using the same salt that we used when we stored the user's password. So salt is equal to user pwd salt, and then the text will be user pwd. And then we are going to, I guess I can use some Java terminology here. I could say assert equals input hash, and then the expected value would be the contents of pwd.dv. So if the two hashes are the same, once again, we can conclude that the inputs are the same. So assert equals will essentially, this is just short form for saying if this doesn't pass, break or throw an error or something. In C, we will simply just do an if-else statement, but for the pseudocode, I'm just going to have assert equals, and this will return false if, it'll return false if they are not equal. Okay, so once we have passed assert equals, that means that the passwords are good. So we need to free user pwd memory, just so we're not storing it. And then now we need to generate our data key. So we first need to, well, I should say this as a pretense, before all these sequences, we're going to be assuming that we have all of these salts and IVs on hand. That will be, I guess I should say this now, but that should actually be step one. I'm sorry. We need to read salts and IVs from iv.dv. So that should be the first step, and then the second step will be validating the password. So I'm not going to go into the details here, but we're essentially just going to read in bytes or blocks of 16 bytes and take them in one by one in this exact order here. So I'll just I'll put that in afterwards. So we need to free the user's password, because we don't want to store it in the RAM. So free the password, and then now we're going to generate our encryption key. So we have validated the user's password. 3, generate or decrypt data key. So we first need to generate or derive our key encryption key. So key encryption key is equal to pbkdf2, same algorithm as before, the same call as before. The key is equal to user PWD. We have to free this afterwards. My mistake. Cannot free that beforehand. So we use the user's password as the key. The salt is equal to KEK salt, and then the derived key length is equal to 32. So then once we have derived this key, we can now free the user's password because we don't need it anymore. So we have the key encryption key, and then now we're going to decrypt data key. So we're going to decrypt data key. So data key is equal to AES decrypt 256. I should actually specify that this is encrypt. So decrypt AES, or decrypt using the AES algorithm. The K is equal to the same key as above, key encryption key. The text is equal to the contents of datakey.dv. Because we're now taking the encrypted contents, the encrypted password, and we want to put it into plain text so that we can use. And then the IV is also the same as above. So IV is equal to data key IV. One thing to note here is that we have to use the same key and IV pair here because these two functions have to be perfectly inverse of each other if we want this to work. So when we write the data key, when we write the encrypted data key, we pass in the key encryption key as the key, and then the data key IV as the IV, and that will give us a unique output. If we use a different IV to decrypt, it would not give us the same output. So we need to make sure that the same parameters are being passed in. So now we have data key on hand, which is good. Next thing we're going to do is we're going to generate the AES key schedule. So the big thing that we need to think about is in the AES code that we wrote, the key schedule, which if you want more details on that, watch the AES video. The key schedule is generated every time we call AES encrypt or AES decrypt. In our application, since we're going to be using the same key every time, or the same data key every time, we're just going to want to have that key schedule stored in memory somewhere so we don't have to regenerate it every time. So I added a bit of compatibility for this so that you could pass in a key schedule after the video pretty recently, actually. So that should be committed to the C Mathematics library, the C Mathematics repository, but we will be generating the AES key schedule and putting it into in our application structure. So we'll say key schedule is equal to AES generate key schedule 256 with K is equal to data key. Since now we want to generate the key schedule for data key. For AES decrypt 256, we're going to just generate that key schedule every time for key encryption key because we're storing it, because we're only using it this once. We're not storing it permanently in our memory. So I also need to, once we decrypt the data key, we need to free key encryption key. Okay, so that's generate the key schedule. All right, next we are going to allocate memory. So we're going to have our 3 maps. If we look at the files example, like I said before, so the way we're loading in data is upon initialization, we are loading in these 3 map files. So map.dv, btree.dv, and category.dv. What these files will help us do is it will help us organize our data in data.dv. So data.dv can be a massive file and we don't want to load all of it in at once. So we're going to load in these abstracted versions of the data when we start our program, and then this is enough data, enough information to help us read data.dv properly and get the data when a user requests it. So we will allocate memory to the maps. So this will be the name map, the B tree, and then the category map. So name map is equal to, I believe I have it as an AVL tree. B tree is just a B tree. So I should actually name this initial block map. So that's just a B tree, and then category map is also equal to an AVL tree. Okay, we have allocated our memory to the maps now, and now we're going to actually start parsing data from the data files, or from the 3 abstracted files. We will start with btree.pwdefault, or .dv, sorry. So decrypt and load btree.dv. So we'll start by getting the contents. Btree string is equal to contents of btree.dv. So we're just getting the file contents there, and we're going to decrypt it using the IV that we have for the B trees. So we're going to call AES decrypt 256. Our key is equal to data key once again. So K is equal to data key. The text is equal to the contents of btree.dv, and then the IV is going to be equal to btree IV. And then for each, the way we're going to parse it is exactly how we outlined it in our diagram last time. So 4 bytes for an ID, and then 4 bytes for an initial block, and they're just both integers. So we know it's going to be 4 bytes each. So we will, for each entry, read 4 characters. And the notation I'm going to use here is just read 4, and then characters will be the variable name that we read it into, where 4 is the size. So it'll just be read 4 characters, and then ID is equal to the value of the characters, so the array characters, and the base is going to be 256. So this is just how we're going to parse the integer. And then one thing that we're going to have to note or start processing here is a maximum ID. So we're going to read entries, and we want to find the maximum ID of a function, or of an entry, because when we add new entries, they need to have unique IDs. So we're going to do something like an auto unique thing, where we're just going to increment from the maximum ID. So we're going to have our structure, and we'll have a max ID attribute, which will just be the maximum of ID in the existing maximum ID. And then we read another 4 characters, and then the ID is going to be the integer value of the characters with base of 256. And then we insert the key value pair of ID initial block. Sorry, the second group of 4 characters should be in the initial block. So we insert the key value pair ID initial block into entry map. And the initial block map should actually just be called entry map. The btree entry map. So that's the btree file. Now the next file is going to be map.pw.dv. So decrypt and load map.dv. So once again, we're going to decrypt the contents. So map string is equal to AES decrypt 256. Key is equal to data key. The text is going to be the contents of map.dv, same as before, and then IV is equal to now map IV. So this call is almost the exact same as btree string, except we're using different contents from a different file and a different IV. Now, the way we process the map is right here we have our name, which is a string until we hit a terminator character, and then we have a 4-byte ID. So we're going to do for each entry, we're going to read characters until a \0. So the name will be the characters, just the string itself. We don't need to process it or parse anything. Then we read 4 characters. And then here, ID will be the value of those 4 characters with base 256. And then after this, we insert the key value pair name ID into name map. So the name is going to be mapped to an ID in the name map, and then the ID will be mapped to an initial block in the entry map. And then the last file here will be 8, or so step 8 will be decrypt and load categories.dv. Once again, we're going to get the string. So categories string is equal to AES decrypt 256. K is equal to data key. The text is equal to the contents of categories.dv. And then the IV is equal to is equal to category IDV. And then we go through each entry. So for each entry. Now for categories, it's going to be something very similar to map.dv, except we're reversing the role. So we read one character as the category ID and then a string for the name of the category. So read one character, and then ID is equal to the value of that character in base 256. And then read characters until we get a terminator. So the name will be that character string. And then we insert the key value pairs ID and name into category map. I was thinking about this. We also need to actually go the other way around. Or should it just be name ID? Because when a user requests data, they're going to be passing in the category name, so they'll be passing in password, and we need to tell the processor or the data parser which category ID to look for. So it's useless to map the ID to the name. We need to map the name to the ID. Okay, that sounds more right. So the category map is going to be another AVL tree where we map a name to an ID. So those are the steps for logging in. So we have read the salts on the IVs from the IV file. We need to validate the user's password. Then we need to decrypt the data key by generating a derived key from the user's password, and then decrypt our random key using the derived key. And then we generate our AES schedule to be used throughout the execution of the program. Then we allocate our map memory, and then we decrypt and load each of the abstraction files in our specific way. Okay, so that is reading. Now what about writing? So we're going to break logging out into two different steps. So we're going to save the memory first, and then we will also free. I'm going to put save as a different sequence just because there may be a point where a user just may request to save data. It's pretty simple. You don't always want to wait until log out or until logging out to save your updated data. So for example, if we added a bunch of entries, we wouldn't just want to keep that in the RAM without writing it every so often. So we're going to have a separate sequence to save the memory, and we'll work on the saving first, and then we will do the logout sequence. So saving here should be pretty somewhat standard. So we have the first one, it's just going to be writing the 3 abstraction files. So we need to stringify and encrypt entry map. Once again, entry map is going to be this map here where we map a name to an ID. So we're going to stringify. So for each entry, this is just going to be traversing the AVL tree. So we're going to say entry string is equal to, so for the format for each entry here is it's going to be a string then a name, or a string then an ID. So it will be the, sorry, this is entry map. This is the, I want to do a name map first. So name map, we're going to get the entry string will be the entry.name, a \0 for the terminator, and then the small endian representation of entry.id. So I will go over the specifics of how we're going to read and write integers, but we're going to keep it as small endian throughout for consistency. So that's for each entry, and then we concatenate entry string to name map string. And then afterwards, we're going to write the encrypted version. So write AES encrypt 256. The key is equal to data key. The text is equal to entry string, so that all the concatenated values. And then the IV will be the same IV as before, map IV. And this will be right into map.pwd vaults. Or sorry, .dv. I have different names in my reference. Okay, so it's going to pretty much go like this for the other two files. So I'll just go through this somewhat quickly. Second one is going to be stringify and encrypt entry map. So this will be the B tree here. So for each entry through a traversal, the entry string is equal to the small endian version of entry.id, and then the small endian version of entry.initialBlock. And then we concatenate entry string to B tree string. And then after our traversal, we're going to write AES encrypt 256 using the same data key. The text is now entry string, and then the IV will be B tree IV. And this will be written into btree.dv. And then finally, we have our categories map. So stringify and encrypt categories map. So we'll go for each entry string is equal to, so now for the categories, it's just a 1-character ID and then a string for the name. So entry string is equal to the small endian of entry.id, but that will just be 1 byte. And then entry.name, and then a \0 for the terminator. And then we concatenate entry string to categories string. And then after that, after the traversal, we're going to write the encrypted version using data key. Text is equal to categories string, and this, I made a mistake with the name up there. This should be B tree string instead of entry string, and then the IV will be categories IV, and this will be written into categories.dv. Okay, so that's the save sequence. So 3 steps there, which are the exact inverses of the last 3 steps of the login sequence. All right, and then logout. This will be pretty simple. We're going to call save. So 1, call the save sequence, because once we log out, we want to save all our data. And then 2, we're going to be freeing memory in general. So we'll call free on data key, free the key schedule, free B tree, or sorry, we're going to call B tree free on entry map. Then we'll call AVL free on name map, and also AVL free on category map. And then the last value that we have to set is app, or just max ID, is equal to 0. So we're undoing all of the writing that we did here. We're saving all the memory, and then we're freeing all the data structures. And this max ID, once again, is just what we have up here. So the max ID is just the maximum entry ID, so we just want to reset that to 0 when we log out. And yeah, so that is those are the first 3 sequences that we're looking at. I'm not sure right now, but I think next time we will be looking at a few more sequences, actually regarding the reading and writing into data.dv, and then we'll start progressing into writing some code, integrating our libraries and stuff like that in the future videos. So yeah, hope you guys learned something, and I will see you guys in the next videos. Have a good one.